This little thing here is the same shape as a Raspberry Pi, and it's actually just a breakout board for this little guy here, a $9 RISC-V single board computer. The Milk 5 Duo is a $9 single board computer. It runs Linux, has 64 megs of RAM, and a micro SD card slot in this little tiny package that's so small I can't even show it on camera because I don't have a macro lens. It has an onboard camera connector, it can do encoding of video, has onboard 100 megabit Ethernet, and yeah, what else could you ask for from a $9 single board computer? So today I'm going to play with this and understand the RISC-V architecture, why RISC-V could be the future of computing, and how you can get started with this little tiny $9 single board computer. So let's get started with this adventure. So in case you haven't heard of RISC-V before, it's an instruction set architecture which competes against things like x86 or the ARM instruction set. Essentially, that's a specification for the machine language of a processor. Originally designed by UC Berkeley, RISC-V was designed to be an open and royalty-free platform for people to build on. The document isn't particularly long, and the instruction set is not particularly complex, but it's an extremely well thought out and well designed architecture, and all of the design decisions and design logic is included in the document, unlike something like ARM. So it's growing in popularity with a number of niches due to its royalty-free nature and the ability for anyone to produce chips or implementations of the architecture. I'm very excited to play with it, so come along and try it with me. So this little thing is so small that here is a US quarter to compare it against. They also sent a breakout board. This has a USB hub and Ethernet. And Ethernet comes directly off of this board. So this board actually has 100 megabit Ethernet built in, but it doesn't have magnetics and doesn't have a connector, so you need like a mag jack. And then they also sent along this little tiny camera. I don't know if this gives you a sense of scale for this thing. So this chip in this board is essentially designed for security cameras. So it has like H.264 hardware encode, it has the camera interface, and it has 100 meg Ethernet, so that's what it's designed for. But they've packaged it into this nice development board. So this looks just like a Raspberry Pi form factor. So we've got Ethernet, which is 100 meg, USB 2, there's a USB 2 hub here, and then it picks up some pogo pads on the board, and then this is where the actual dev board itself mounts here. There's no micro SD because that's actually on this board itself. Let's see what we got here. Wow, this thing is tiny. Okay, here it is. So we got USB-C. This actually acts as a USB-C gadget. So when you plug it into your computer, it shows up as a USB Ethernet adapter, and you can SSH into the Linux system on here. Some passives and the one chip. So everything is done by this one chip. So I got my tiny little Duo board. I got a really tiny micro SD card, and we're going to image this thing and boot it up in Linux. So coming over here to their docs page. So we probably need official image, which is this guy. So got the image on the SD card. This is a tiny little thing. It's in here. I'll plug it into my computer now over USB, and it should show up as an Ethernet adapter, which is magical. So it's not as simple as it seems, so I have to click Update, Browse. Let me pick from a list available. USB RISC. Go ahead. Don't know why Windows can't figure that out on its own, but Windows is kind of stupid. We've got automatic IP address. That's good. Milk V. Okay. We are in /root. We have a file system. Do we have a GCC? No, we don't have GCC. What bins do we have? So we have busybox. And yeah, not a whole lot else. We have IP. So ETH0 has no carrier. USB has the RISC adapter. So we're connected. Also, I should note it blinks, and there's a script built in that does this blink. So let's take a look at that script and see what it looks like. Okay, so this is what does the blink. So we're using bin sh, we're using GPIO 440. That's another neat thing about this. All of the peripherals on this chip are exported through the Linux kernel's sysfs API. So there are device nodes in the sysfs file system to access all of the hardware on this thing. And the website has some really good documentation on how to access all these files and what they're named. So you can get to the GPIO, the PWM generators, the SPI bus, I2C, all that kind of stuff through the usual Linux interfaces that are designed for this kind of thing. It's really quite impressive to me that it's documented and working to this level on essentially a new board and a new platform like this. I've set up a Linux environment on Debian that has the RISC-V 64 compiler, RV64, and I'm going to use that environment to compile some test programs for this and then copy them over with SSH. So it should be relatively simple. Let's see if we can get the blinking trick to work with the program we write in C ourselves. Then we take a look at what the RISC-V assembly looks like for that same program. So just to make sure our toolchain works at all, I have just a basic hello world. And I'm going to go ahead and build that. So I copied my test file over with SCP, and let's run it. So there we go. Hello from RISC-V. How nice. I did have to tell GCC to link as a static binary. So some of the libraries it was trying to dynamically pull in were not on this little guy here, which is pretty normal for embedded stuff. So if I knew what libraries were on it, I could know what I have to statically link, but I just statically linked the whole binary. And it's a tiny binary, so that's not a big deal. And it runs. Great. So let's see if we can figure out how to emulate the Blinky program, but in C, because I'm familiar with C, and seems like a good test. So it's blinking out in Morse code the message on top, hello from RISC-V. And it's doing it by writing to those device files in sys class GPIO. I went a little bit overboard, but it was a fun night of programming. Coming over to the computer, here's what the code for that Morse code test looks like. So it's kind of a long file because I wrote it all in one file. But top we have I/O functions, so we're writing to the sys class GPIO. So we have to write the direction to out, and if that fails, that means it hasn't been exported yet, which means it's reserved for the kernel. So we call export on it, and then we set the direction again, set direction to out. Then we can open the value file, and we can write a 0 to it. To actually write the GPIO, we just have to write the literal 1 or 0 and F flush to make sure it gets applied. So that's pretty simple. I have all the times based on the official Morse code spec from Wikipedia, because Wikipedia is obviously the clear source on this. Morse code itself is kind of brilliant. It's sort of like Huffman coding, but before Huffman coding was a thing. And so you make a kind of a tree of if you do a dot or a dash or a dit or a dot, what letter it could be. And so the shortest letter is an E, which is just the dit by itself. Then from there you can either add a dot on the end or a dit on the end, and you can just kind of make a tree of what everything is. I represented that tree using this string here where it's literally dots and dashes, and then I can check for the end of the string with a null because you're null terminated. And then I have a pointer array that's a pointer of tables to the A through Z, 0 through 9. So to print a single letter, that's a char. If it's a space, we do a long sleep, and if it's not, then we have to look up what array we need to find from the pattern table. And so if it's a 0 through 9, we have to find the index at the end plus 26. If it's an A through Z, or with the case masked out, we have to get the letter, and otherwise it's invalid and we don't print anything. And then we print out the string we're printing, which is the literal string from the table, like dot dot dash. And then we just go through the array, turn on the pin, wait either the dit time or the dot time, turn it back off, and then wait the space for the next letter. And then we keep going until we reach the null terminator, and then we wait for the end of letter delay. And then the Morse function is pretty simple. It takes in the string pointer and just goes through every element in the array and prints it, and then goes to the next letter. So now that we've seen the code, let's see how much different RISC-V assembly is from, say, x86 that we're all familiar with. I mean, you're probably not familiar with x86 assembly, but if you were, they're going to look drastically different. So as you may have noticed up here, I actually compiled this for 5 different languages, all of them 64-bit. So we have AMD64, ARch64, which is ARM, MIPS64, PowerPC 64, and RISC-V 64. So let's find void Morse and all of these guys. It's Morse letter. There's Morse. So in x86, you can see here, so this is the address in memory. This is the byte. So this is the value in memory, and this is what the assembly decodes to. So this stuff is just setting up a stack frame for our functions. So we have instructions of variable lengths. That one has 1 byte, this one has 3 bytes, that one has 2, this one has 5. In case you're curious, the longest instruction in x86 is 15 bytes. So in that case, that's a call instruction, and it's not even going that far, it's going to 13F2. You'll notice that these are register names here. x86 likes to name them, so RBX is the base pointer, RDI is the destination register, EDI is extended DI, and RDI is long DI. I don't know why they chose R for that, but R means it's 64-bit, E means it's 32-bit, and nothing means it's 16-bit. Also, fun fact, 16-bit instructions are still a thing in x86 because we have to have backwards compatibility back to the 70s, right? These nice little annotations here show us where branches go. So in this case, the pop is, well, the JE here is taking us down to the pop. So the pop is unwinding the stack frame for the ret. And these are relatively short instructions, but the call can be quite long. So in ARCH64, we again find void Morse. And this time we have much longer instruction words. So in ARM 64-bit, every instruction is 32 bits wide. So like this x86 thing where we have variable numbers of bytes, always 64-bit, and that makes designing the processor a lot easier because you can guarantee things like how long the instruction decode has to be. The instruction decode couldn't potentially have like to straddle a page or something like that. It's simpler from an implementation perspective. So all of this work just to set up a stack frame, so it's not as efficient as x86 was. This one for some reason doesn't want to show the nice jumps. I don't know why this version of GCC doesn't. But again, it's relatively simple. We're going through a loop. We have some instructions. So BL is branch and link. Jumping to Morse letter. So BL means we're going to come back here because we're linking with the link register. CBNZ does a compare with 0 and branch. And that takes us to RISC-V. So RISC-V can have either a 16-bit or a 32-bit instruction, but other than those two lengths, it's not variable. So the front end only has to deal with these two possible cases, and not like x86, where you could have any number of bytes from 1 to 15. So this is us setting up our stack frame. So we're changing the stack pointer, storing the return address. So beak Z, so branch equal to 0. So basically here we're loading in the value that the string points to, and checking if it's equal to 0, which will skip the loop. Because if you remember in our code, we're saying while it's not equal to 0, so while the character is not null. So this is loading the character, and then if it's equal to 0, we do a jump down here to the end. And then we do the loop, and then again in the loop, we check to see if we're 0 and jump back up. So like ARM, we have these branch compare instructions. So this is where we highlight a bit of a big difference between the different instruction sets in how they handle testing and branching. So one of the most fundamental things about an architecture is how it handles memory access, branching, jumping, and math, because those are basically the fundamental things of computer programming. Accessing our data in memory, doing arithmetic on it, we can basically boil down every math operation into its most basic form, and also control flow, where the program code should execute and what path it should take. So the Intel x86 way of doing it probably dates back to some very old processors and how things used to be done in the olden days. Essentially back then, you would have a condition flag that had a couple of bits that were like the state of the processor. And traditionally, these were N, Z, V, and C. So N is if the output was negative, Z is if it's 0, V is if there was a signed overflow, and C is the carry flag, which means there was an unsigned overflow. Some processors didn't have the V bit. PowerPC has a positive bit and a negative bit that are separate. So they have positive, negative, 0, and carry. Basically, processors have flags like this that you can do logic on. So in x86, you do test, and you compare some register value or some memory value, and then you branch based on the results of the test. So first you have to take your value and test it, and that sets the condition bits. And then you can say branch if not equal, branch if equal, jump if equal, whatever your control flow is going to do based on your test. ARM does it a bit differently. So in ARM, the testing is done in the instruction, but it can only compare to 0. So with x86, you can compare two numbers and say who's greater, who's less, whatever. In ARM, you say, is it greater than 0, equal to 0, less than 0, and those are basically your only options. Greater than, equal to, those kind of combinations. So in ARM, what you do is you take the two numbers you want to compare and you subtract them, and then you say, was it positive, was it negative, branch if positive, branch if negative, branch if 0. So since we're counting a null, we can just load that value directly in and say branch if not 0 or branch if 0. And so that's a pretty efficient way of doing it. We don't have to do a test. The way PowerPC does it is they use flag bits similar to Intel, but they always set them at the end of the instruction. So if you do, for example, do an add, you can say add dot. And the dot means whatever the result is, update the condition bits based on that output. So if we add two numbers together and the result was positive, we'll set the positive bit, we'll clear the 0 bit, that kind of thing. And then PowerPC also has this neat trick where it has 8 different condition registers, and you can do Boolean arithmetic around the different condition registers. So it's very common to store Boolean values in condition flag bits and kind of use them as extra registers, which is pretty neat. And I don't think any other system does the 8 condition registers like PowerPC does. And RISC-V takes a similar approach to ARM, where the comparison happens in the instruction. So you don't need a separate test instruction, and you don't have condition bits at all. The instruction reads a value, and it says branch if not equal, branch if positive, branch if negative, etc. like that. So you have to do subtract first, just like ARM. And that's pretty much the solution that most of the RISC architectures have come to, except for PowerPC. So MIPS does it the same way, and MIPS was largely a pioneer in this. Having only 34 instructions, they don't have room for a test instruction. So in case you're curious and you want to read any of this assembly yourself, I've created a GitHub repository, link down below, also link to my blog post about this. And that'll have all of the assembly and the example code I've used if you want to dig into it and read it yourself. So with this board having the full-on computing power of Linux, you might think it doesn't have the I/O of a more embedded microcontroller like a Raspberry Pi Pico. But in fact, that's not true. So in addition to the GPIO that I've already shown, it has a number of hardware PWM generators. It has 5 UARTs if you want to do stereo. It has hardware SPI, including Linux SPI support. It has 3 I2C buses, also integrated with Linux. It has 2 analog inputs, which are 1.8 volts. But the little board has resistor dividers to take in 3.3 volts. And it also has SDIO, which is capable of being used for Wi-Fi. It includes the drivers for that on board as well. So next up, I want to play with Ethernet. So these little pins on the side are Ethernet. So we have a TX differential pair, RX differential pair, and a ground. And they need magnetics to work. You can't just hook this straight up to an Ethernet line. The PHY transceiver is on board, but we just need magnetics. Normally that would be a mag jack. So this is a mag jack. So inside the jack, there's the pulse transformers you need. If you're not using RJ45, you can put a pulse transformer on the board. Or if you have like a multi-way RJ45 connector, you can put pulse transformers on the board. So this breakout board has the pulse transformers in the jack, and it has these pogo pins that can pick up the 5 Ethernet lines. It also has the USB chip that picks up the 2 USB data lines and power from the headers. So we get 4 USB 2 ports. There's also a bunch of extra pads here for extra functionality that's not included by default. So up here we have the diodes and the power supply and inductor you'd need to build a PoE supply. So the parts for this are in the schematic, which is freely available. There's also space for a number of other transceiver chips here, including a SPI bus CAN transceiver, an RS-485 transceiver that uses one of the onboard UARTs, as well as some SPI flash memory. So an assortment of good stuff on this board that's not populated. What is populated is USB-C power, our UART, USB, and Ethernet. But I want to use the USB as the gadget so I can continue to use my SSH method to connect to it. So I taped over the pads on the back for USB. And I'm just going to set this down in here and tape it so I don't have to solder pins on. Because I have another project where I want to use this as is, so I don't want to get solder in all these holes just yet. Seems to be sturdy, so we're holding down those pogo pads. And I just need to bring in Ethernet and USB-C. There we go. So I got it set up for Ethernet, and let's see what we get. I need a little bit of help here, so Mr. Sherlock had to come join me. So if I just run IPA, what do I get? So we're up, and we got an address. Beautiful. But what we don't have is IPv6. So what do we say when we don't have IPv6? We build the kernel ourselves. So I got the shirt on today. So here on GitHub, to have the entire repository needed to build the SD card image. This includes everything in the image. So we've got Linux, we've got U-boot, FreeRTOS, they have an option for that as well. Build root, everything is here. Oh, I lost my help. No more help anymore. So they are suggesting Ubuntu 20.04, and I chose to use Ubuntu 22.04 instead. And I created a container on Proxmox and followed all these instructions, and they worked. The only problem I had building from their instructions was that the version of make image that comes with the host tools that they distribute, so they distribute precompiled RISC-V compilers for Linux. The make image version is designed for Ubuntu 20's libraries. So with Ubuntu 22, it needs a newer version of libSSL. So I just replaced that version of make image with the version from U-boot tools from the Ubuntu package. All good. So at this point, I could run menu config and change IPv6 to enable and recompile the kernel. And eventually we had the message, gen image successful. Then I can flash that onto my micro SD card and go from there. So I got my custom Linux kernel on this SD card, and let's go. Ooh, wow, look at that. So I got my IPv4, got my IPv6, got my link local, and I got a link local here. So now can I ping 6 Google? Okay, so that worked. So we connected to an HTTP site over IPv6 on port 80, because remember, we don't have TLS, so we can't do TLS. But it did make an IPv6 connection to the outside world, and it succeeded. So if I were to write my own app that did whatever protocol I want to do, I could write that using IPv6 on this board. And that's really magical to me. So now that it works, I committed my changes to GitHub and sent them a pull request saying IPv4 is legacy. So I decided to try testing USB as well, which meant I had to solder pins on. So it's currently running a USB flash drive, and this is a USB Zigbee dongle I had on hand. It should show up as a serial port if it has a driver for it. Of course, I had to connect over Ethernet since I can't use the USB gadget when I'm using USB host, but that's expected with only one USB controller. So over here in PuTTY, so SDA 1, 2, and 3, that is my flash drive. Other cool things you can see, the SPI dev shows up, so there's 2 SPI buses, and they both show up with Linux SPI devices. There's 5 UARTs, and they all 5 show up here. What does not show up is the UART for that Zigbee dongle. So I'm guessing that that would be another kernel compile thing to enable that driver on this minimal Linux build. So the only hardware left to test is the camera. In case you're curious about the camera module, which is currently selling for $3.50. It is a Galaxy Core GC2083, resolution 1920 by 1080, and it can do that 30 frames per second. Comes with example software for the board that streams it over RTSP, and that's what I'm using now to collect it. So if you want to build your own security camera, this is a pretty cheap option. So that ends my tour of the Milk-V or Milk-V Duo, the $9 RISC-V single board computer. I'm not sure if you know this about me, but I actually have a degree in computer engineering. So writing programs in assembly and optimizing them is kind of my jam. And so my professional experience includes things like writing and debugging and optimizing at the assembly level, code in ARM and PowerPC. And so I've written high integrity boot code for some systems in PowerPC assembly. I've done math optimization of complex math functions down at the assembly level or optimizing C level. And that's something I really enjoy. And so working with RISC-V has given me a true enjoyment for computer architecture, again, something I don't see a whole lot in the world. And so as I work with more architectures, I get really sad that x86 that we ended up on, because it's honestly the worst to work with. MIPS is incredibly clean and optimized, but almost too small. It pushes too much work on the compiler. The goal with MIPS was to push clocks as high as possible and make the processor as simple as possible. And that worked to a point, but eventually high-performance computing surpassed it. And so if I wanted to work on MIPS today, I would basically be buying like an old SGI workstation, like an Onyx or a Indy or Indigo or something like that, which isn't really modern. On the PowerPC side, it's technically a RISC or reduced instruction set architecture, but with about 600 instructions, it's getting up there in terms of what you can count as reduced. I really enjoy working with PowerPC as well. It's an excellent architecture to play with, and you can clearly tell it's been designed for high performance computing. And so if I wanted to play with one of those at home, my option would basically be buy like an IBM Power 9 or Power 10, which would be wildly expensive. There is one company that makes PowerPC workstations, but they're also not cheap. With RISC-V, I got the $9 board. I can do architecture learning, assembly, that kind of thing, on a well thought out, well designed architecture that's not the bottom like MIPS. It's designed for high performance and expandable, and I really like that about RISC-V. There are also, of course, higher end boards in this $9 board. This particular company also has 2 different Raspberry Pi form factor boards with higher end processors, and they're working on coming out with a full-on 64-core workstation. So maybe someday I'll be able to afford one of those, but for now I've got this guy. And so great to see you all. If you want to buy one of these, I have links in the description where you can get them. You do have to pay for shipping from Asia. I am doing a group buy as well over on my Ko-fi, so link in the description for my Ko-fi. And in my store there, you'll find some of these boards that I bought myself, and I'm reselling just to help out shipping for Americans. If you're outside of America, it's probably easier to buy direct from them. If you want to talk to me about anything, head to my Discord server, link down in the description for that as well. Thanks for coming, and as always, I'll see you on the next adventure. Next project for this board, I got a beautiful box from Ukraine that includes 12 old used audio parts, so stay tuned to see that.